Let's talk about the moment of force. And the moment of force is basically if I've got a force located at some distance away from a point. Okay, that force has a tendency to want to rotate, about that point. Okay, sometimes we refer to this as a torque. In engineering, torque is a very specific kind of moment, and we'll clear that up when we get into mechanics of materials. So we call them moment. You may have heard of them as torques in the past. But again, what it essentially is this force causing rotation because it's some distance away from point O. So I'm creating this rotation about my z-axis here, this force being some distance away from point O. Okay? Now the magnitude of a moment is that force times the perpendicular distance, a distance that's perpendicular to the force. Okay? And take that force times that distance, that perpendicular distance, that creates the magnitude of the force. So this would be F times D, the moment about Z in this picture that I have here. Now, if my force for some reason is not perfectly perpendicular, okay, to the distance D on this wrench, say it's at an angle of theta, okay, that perpendicular distance is actually d sine theta. Again, this is opposite of the theta, so it's d sine theta. That is actually the force. Notice that this moment arm is smaller than the moment arm here, even though it's the same force, so I would create less moment here than I would here, right? The bigger the moment arm, the bigger the force. Or, excuse me, bigger the moment of the force. Okay. Likewise, the bigger the force, the bigger the moment's going to be. Okay. Now, the other way we can think about this is breaking the force into components instead of the distance into components. I could have a perpendicular force here. Again, that would be F sine theta, and a inline force, F cosine theta. And that force would go right through point O. And if a force goes right through point O, it actually creates no moment about that point. I need that perpendicular distance to create the moment about a force. So any force that goes through a point creates no rotation, creates no moment about that point. So we're always looking for that perpendicular component, especially when we're dealing in two dimensions. So that takes care of the magnitude, which is just the force times the perpendicular distance. Okay. Now the direction, moment is also a vector, and that vector is going to be perpendicular to the plane that contains my moment arm and my force. Okay, we use something called the right-hand rule to determine what's positive and what's negative when it comes to moments. Okay, so if I take my right hand and I curl my fingers in such a direction that moment is creating, okay, the thumb of my right thumb is going to point in the positive direction. So again, the moment vector is actually a rotation. Okay, but we have to give it a direction based on which way our thumb is pointing on our right hand as it rotates around. So in two dimensions, like I have down here, okay, if I'm moving counterclockwise, we call that a positive moment. And a counterclockwise, if I use my right fingers and try to curl them in a counterclockwise rotation, my thumb actually points out of the screen. So counterclockwise, my thumb points out of the screen, the vector points out of the screen. We call that a positive moment. Conversely, going in the counterclockwise direction, okay, if I curl my right-handed fingers clockwise, my thumb points into the screen. We call that the negative moment. Okay, so clockwise is negative. That creates on my right hand, thumb into the screen. Okay, negative moment. So remember, counterclockwise positive, clockwise negative. Okay. Okay, so a couple of things that's going to help us in calculating 2D moments. The first idea is this idea of transmissibility. And what that means is that I can draw my moment arm from point O to anywhere along the line of action of the force. And this is going to help me to find my perpendicular distances. Okay. Now, I have this written in vector in 3D form. We'll talk about that next time. But just know that R cross F is the same thing as the moment arm times the force. Now realize, regardless of which moment arm I use, R1, R2, or R3, I'm going to get the same moment. Okay, so I can draw, in drawing my moment arm, I can draw my moment arm from point O to anywhere along the line of action of the force. Okay. Now, the next thing that's going to help us is the idea of resultants. Okay. Moments are vectors, just like forces, so I can sum them up just like I sum up forces. Okay, and a resultant moment is nothing more than summing up all the forces times all of the perpendicular distance in 2 dimensions. Okay, so using both this idea of resultants as well as that idea of transmissibility, where I can draw the moment arm from point O to anywhere along the line of action of the force, we get the idea of the principle of moments, which is what we're going to use in 2 dimensions to help us figure out what these moments are. And that statement is simply that the moment of a force is equal to the sum of the moments of the components of the force. So what does that mean? So I've got force, this blue vector right here, the force F, and I want to find the moment about point O. Okay? So rather than finding this perpendicular distance d, oftentimes it's actually easier to break that force up into horizontal and vertical components, the x and the y components, and then using this transmissibility, drawing 2 separate moment arms to each of those 2 components. So for example, this horizontal component, okay, the line of action is all the way along this horizontal line. I can draw this vertical distance to this point along the line of action. That's my perpendicular distance that I call y. Similarly, my vertical force, Fy, okay, it has a line of action all the way along this vertical line, like so. I can draw using the transmissibility idea, I can draw a moment arm from O to that vertical line of action. That would be a distance x. Okay. Using the resultants idea, I sum up those 2 moments to get the total moment of F. Okay, so I take the horizontal, well, let's how I have it here. I take the vertical force times the horizontal distance. Okay, that gives me 1 component of the moment. Then I take the horizontal distance the horizontal force times the horizontal distance. So I get x times Fy and y times Fx. Now, Fy creates a counterclockwise moment, so that would be a positive. Fx creates a clockwise moment, so that would be negative. And that's where the plus and the minus goes in here. Don't worry about that. It's going to be different for every problem. For this specific example, it'll look like this. But what I want you to be aware of is the way we oftentimes do this, and we'll do this in the example, we break the force up into x and y components. Okay, take the x component of the force vector times the y distance, and take the y component of the force times the x distance to get those perpendicular components. Then the plus and minus, you just look at the force to figure out whether it's in the positive or negative direction.